Hi students, I'm Praveen Sebastian Paul. In this lecture, we are discussing what is an extrinsic semiconductor. An extrinsic semiconductor is one that has been doped. During the manufacture of the semiconductor crystal, a trace of element or chemical called a doping agent has been incorporated chemically into the crystal for the purpose of giving it a different electrical property than the pure conductor crystal. In an extrinsic semiconductor, it is these foreign dopant atoms in the crystal lattice that mainly provide the charge carrier which carry electric current through the crystal. The doping agents used are of two types, resulting in two types of extrinsic semiconductor. An electron donor dopant in an atom, which when incorporated in the crystal, releases a mobile conduction electron into the crystal lattice. An extrinsic semiconductor, which has been doped with electron donor atom, is called an N-type semiconductor, because the majority of the charge carrier in the crystal are negative electrons. An electron acceptor dopant is an atom which accepts an electron from the lattice, creating a vacancy where an electron should be called a hole, which can move through the crystal like a positively charged particle. An extrinsic semiconductor which has been doped with electron acceptor atom is called P-type semiconductor, because the majority of charge carrier in the crystal are positive holes. Doping is the key to the extraordinary wide range of electrical behavior that the semiconductor can exhibit, and extrinsic semiconductors are used to make semiconductor electronic devices such as diode, transistor, integrated circuits, semiconductor lasers, LED, as well as photovoltaic cells. Sophisticated semiconductor fabrication processes like photolithography can implant different dopant elements in different regions of the same semiconductor crystal wafer, creating semiconductor devices on the wafer's surface. For example, a common type of transistor, the general one is NPN bipolar transistor, consists of an extrinsic semiconductor crystal with two regions of N-type semiconductor separated by a region of P-type semiconductor with a metal contact attached to each part. So now we have to discuss what are the conductions in semiconductor. A solid substance can conduct electric current only if it contains charged particles like electrons, which are free to move about and not attached to atoms. In a metal conductor, it is the metal atoms that provide electrons. Typically, each metal atom releases one of its outer orbital electron to become a conduction electron, which can move about throughout the crystal and carry electric current. Therefore, the number of conduction electrons in a metal is equal to the number of atoms, a very large number, making the metal a good conductor. Unlike in metal, the atoms that make up the bulk semiconductor crystal do not provide the electron which are responsible for conduction. In semiconductors, electrical conduction is due to the mobile charge carriers like electrons or holes, which are provided by impurities or dopant atoms in the crystal. In an extrinsic semiconductor, the concentration of doping atom in the crystal largely determines the density of charge carriers, which determines its electrical conductivity, as well as a great many other electrical properties. This is the key to semiconductors' versatility. Their conductivity can be manipulated over many orders of magnitude by doping. When it comes to the semiconductor doping, the semiconductor doping is a process that changes an intrinsic semiconductor to an extrinsic semiconductor. During the doping, impurity atoms are introduced to an intrinsic semiconductor. Impurity atoms are atoms of different element than the atom of the intrinsic semiconductor. Impurity atoms act as either donor or acceptor to the intrinsic semiconductor, changing the electron and hole concentration of the semiconductor. Impurity atoms are classified as either donor or acceptor atom based upon the effect they have on the intrinsic semiconductor. The donor impurity atom have more valence electron than the atoms they replace in the intrinsic semiconductor lattice. Donor impurities donate their extra valence electron to a semiconductor's conduction band, providing excess electrons to the intrinsic semiconductor. Excess electrons increase the electron carrier concentration of the semiconductor, making it as a N-type semiconductor. So, the acceptor impurity atoms have fewer valence electrons than the atoms they replace in the intrinsic semiconductor lattice. They accept the electron from the semiconductor's valence band. This provides excess hole to the intrinsic semiconductor. The excess hole increases the hole carrier concentration of the semiconductor and thus creating a p-type semiconductor. The semiconductor dopant atoms are defined by the column of the periodic table in which they fall. The column definition of the semiconductor determines how many valence electrons its atom have and whether the dopant atoms act as a semiconductor's donor or acceptor. The group 4 semiconductor uses 5 atoms as donors and group 3 atoms are acceptors. The compound semiconductors uses group 6 atoms as donor and group 2 atoms as acceptors. The group 3 to 5 semiconductors can also use group 4 atom as either donor or acceptor. When a group 4 atom replaces the group 3 element in the semiconductor lattice, the group 4 atom acts as a donor. Conversely, when a group 4 atom replaces the group 5 element, the group 4 atom acts as an acceptor. The group 4 atoms can act as both donor and acceptor, therefore they are known as amphoteric impurities. So my dear students, this table shows the group 4 as well as group 3 to 5 semiconductor properties. In the group 4, the intrinsic semiconductors are silicon and germanium, and if these silicon and germanium are designed to an N-type semiconductor, then the donor atoms are phosphorus, arsenic and antimony. If this silicon and germanium has to be changed to p-type semiconductor, we should add some impurities with boron, aluminum or gallium. In the case of group 3 to group 5 semiconductors, the intrinsic semiconductors are aluminum phosphide, aluminum arsenide, gallium arsenide and gallium nitride. And if we want to convert this intrinsic semiconductor into N-type semiconductor, we should add the donor atoms like selenium, tellurium, silicon or germanium. But if we want to convert this to p-type semiconductor, we should add acceptor atoms like beryllium, zinc, silicon, germanium or cadmium. So this shows how a semiconductor, that is intrinsic semiconductors, can be converted into an extrinsic semiconductor. So my dear students, now we are discussing what are the uses of extrinsic semiconductor. The extrinsic semiconductors are components of many common electrical devices. A semiconductor diode consists of p-type and n-type semiconductor placed in junction with one another. Currently, the most semiconductor diode used doped silicon or doped germanium. The transistors also make use of extrinsic semiconductors. The bipolar junction transistor, that is a BJT, which amplify the current, are one of the type of transistor. The most common BJT are NPN or PNP type. The next one is a field effective transistor, that is FET. So these are the another type of transistors which amplify the current, implementing the extrinsic semiconductors. So another different common implementations are lasers, solar cells, photodetectors, light-emitting diodes, that is LEDs, and Thyristors. So my dear students, in this lecture we had discussed what are the extrinsic semiconductors. So my dear students, as we mentioned, there are two types of extrinsic semiconductor, the N-type and P-type semiconductor. We will discuss in detail of these two types in the upcoming lectures. So my dear students, hope you had understood this topic. So my dear students, kindly go through the assignment question. Our question is, write notes on extrinsic semiconductor. So my dear students, see you soon in the upcoming lecture. We will discuss what is an N-type semiconductor. So dear students, see you soon. Until then, goodbye. Thank you and all the best.